All right, so we're very pleased to have Jeremy Lovejoy speaking today from University of Paris and CNRS. And he'll be speaking to us about a problem of partitions, which is interesting to many of the people here. In particular, he'll be talking about parity bias in partitions.
Okay, so thanks for the introduction. Thanks for putting on this seminar too, and thanks for putting the videos online for everybody to watch, because especially for me, 9 o'clock California time is not ideal. So I've been watching everything online. So if you've seen me talk in the last few years, you've seen me talk about mostly about quantum knot invariance. I got the feeling that was becoming a bit heavy, so I want to do something a little bit lighter. So this is some kind of classical partition theory called parity bias in partitions. Hopefully this will look fairly light and elementary. There's a lot of combinatorics. Some of it's heavy duty, but I'll skip over that. And then there's some interesting asymptotics and open questions at the end. All right, so there's two goals to this talk. First, I want to describe the results in our paper. So this is joint work with Byungchan Kim and Eunmi Kim, both in Seoul. The paper is called Parity Bias in Partitions. It appeared in the European Journal of Combinatorics in 2020. I think they don't do page numbers anymore in the European Journal of Combinatorics. There's some kind of code number with it. But anyway, it's volume 89. So that hopefully will take me about 35 or 40 minutes. And then for the rest, some conjectures. So our study of parity bias led to some interesting conjectures, one of which appears quite related to conjectures of Andrews on certain Q series in Ramanujan's last notebook. And to my knowledge, these conjectures of Andrews are still open. So I'd like to talk about those conjectures toward the end, show you some data on Maple, and show you Andrew's paper and mention some things in his paper. So I've kind of been out of the loop for the last year. So as far as I know, these conjectures of Andrews are still open, but maybe somebody without kids or with grown kids has been working and made some progress, but I don't know about it. Okay, so those are the two main goals. So let me start by talking about what I mean by parity bias. So here's two definitions. So let P sub O, that's a subscript O, P sub O of n denote the number of partitions of n with more odd parts than even parts, and let P sub E of n denote the number of partitions of n with more even parts than odd parts. So I don't have much to say here in the way of motivation. Sometimes we just wonder about things. And so it was natural to wonder about functions like this, counting partitions with more odd parts than even parts. And it turns out, and I'll state this as a theorem shortly, that P sub O of n is bigger than P sub E of n, except for n equals 2. At n equals 2, there are only two partitions of n, 2 and 1 plus 1. And so we don't have P sub O of n bigger than P sub E of n. I'm not really sure if this, when I first saw it, I thought it was natural. I tried to think of some kind of general asymptotic or probabilistic results which would make it so. I couldn't think of anything good, but for me, it's kind of intuitive. If you start writing down all the partitions of small numbers, there are a lot of ones. And so that gives heavily to P sub O of n. But let's just say it looks intuitive to me. Okay, so refer to this as parity bias. So this is the tendency of partitions to have more odd parts than even parts. And that's what this talk is all about. So I'll mention this inequality above, and then some more precise results about P sub O of n and P sub E of n. But first I want to do an example. So this is very easy to compute for small n. So I put all the partitions of 6, I hope. There are 11 of them. I'm using my cursor as a pointer, so if you can't see my cursor, let me know. I think it should be okay. And then here, this is not the ratio. Obviously, this is just deciding if this partition is counted by P sub E of 6 or P sub O of 6. So, right, 6 has more even parts than odd parts. 5 plus 1 has more odd parts than even parts. 4 plus 2 has more even parts than odd parts. 4 plus 1 has 2 odd parts, 1 even parts. So it's counted by P sub O, and so on. Not every partition is counted by P sub E or P sub O. This one, for example, 2 plus 2 plus 1 plus 1 has 2 even parts and 2 odd parts, so it's counted by neither. Okay, so hopefully that example is clear. Okay, so we have P sub O of 6 is equal to 7, and P sub E of 6 is equal to 3. And there's one partition which is counted by neither. All right, so here are our results. The results are really clean and easy to state, which is one thing I like about this paper. Don't need a lot of preparation, definitions. There are 3 results. So the first one is for all n not equal to 2 if p sub o of n bigger than p sub e of n. I mentioned that already. The second is a more precise inequality. So for all positive integers n bigger than 7, p sub o of n is between 2 times p sub e of n and 3 times p sub e of n. Okay, so this is true for all positive integers n bigger than 7. And then the third theorem is an asymptotic result, which says that as n goes to infinity, the proportion or the ratio of p sub o of n to p sub e of n goes to 1 plus the square root of 2, which is approximately 2.4142. Okay, so these are our 3 results. I'll say brief words about the proofs, and then I'll go into more detail about the proofs. So as usual, stop me if there are any questions. Okay, so just some key words here. So proof of theorem 1 uses generating functions and Q-series transformations. So this is fairly elementary if you understand partition theory. Theorem 2 uses combinatorial mappings, and this is the really hard part. We had to come up with some injections to prove these inequalities. And part 3 uses classical asymptotic analysis, in particular, Ingham's theorem. All right, so let me give more detail on all these theorems, or a lot more detail, in fact, on some of them. First, I'll fix some notation. So certainly you've seen this in some of the talks. So we use the usual Q-series notation called Q factorial, Q rising factorial, Q Pockhammer symbol, whatever you want to call it. So A semicolon Q sub n is this finite product, k equals 0 to n minus 1, 1 minus a q to the k, a semicolon q infinity is equal to product k equals 0 to infinity, 1 minus a q to the k. Okay, so first I want to talk about some elementary partition theory. So using standard combinatorial arguments, this term here, q to the bn divided by q squared sub n, is a simple generating function, and this is what it counts. So depending on b, it generates partitions into at most n even parts if b is equal to 0, exactly n odd parts if b is equal to 1, and exactly n even parts if b is equal to 2. If you know partition theory, this is quite clear. If you don't, well, 1 over q sub n is the generating function for partitions into parts at most n. So if you think of a Faraday's diagram with dots or boxes and replace each one by a 2, and then read columns, then you get a partition into at most n even parts. Okay, and that's the case b equals 0. And if you like to use zeros, you could say exactly n even parts where zeros are allowed. Okay, and then once you understand the b equals 0 case, then b equals 1 and 2 are clear, because if this one is true, well then here you add 1 to each part and you get exactly n odd parts, and here you add 2 to each part and you get exactly n even parts. Okay, so these are the elementary terms that we'll use to construct the generating functions. So you see if we're counting partitions and we want to count the number of even parts and odd parts, these terms are useful. So let's do this. So you call capital P sub O of Q the generating function for P sub O of n. So this is some P sub O of n, Q to the n. And it turns out to be this. Okay, so why is this? So Q to the n, so take 1 over Q squared sub n. So B equals 0 in the previous slide. That's a partition into at most n even parts. And then Q sub n divided by Q squared sub n is a partition into exactly n odd parts. Okay, so this is at least as many even parts, at least as many odd parts as even parts here. And then this one will be exactly as many odd parts as even parts. And so you have to subtract those out. And then you get P sub little o of n, so more odd parts than even parts. Hopefully you can follow that. But if you go back to the previous slide and just put everything together, that's what you get. Okay, and here's some of the first few coefficients. Not very informative, but it just looks like it's growing like an ordinary, the usual kind of Q series. Okay, so we can do the same thing for P sub E of n. So this, as we remarked above, this is the generating function for partitions with at least as many odd parts as even parts. And so if we take all partitions and subtract this off, then we get the generating function for partitions with more even parts than odd parts. And again, this just looks like an ordinary Q expansion of a Q hypergeometric function. Okay, well then the natural thing to do is subtract these. we're looking for the difference. The problem is this doesn't help. At least it didn't help us. So if you just naively subtract these, we weren't able to prove the inequality we wanted. And so the trick is to use some classical Q-series transformations. So if you know about Q-series transformations, in this case, these were really elementary ones. We use Heinz transformation or some iteration of it. And we rewrite these. So it turns out that P sub little o of Q can be written in this way. So 1 over Q squared infinity, sum n bigger equal to 1, Q to the 2n squared minus n divided by Q squared n, Q squared n minus 1. And P sub little e of Q is similar. It's 1 over Q squared infinity, sum Q to the 2n squared, 1 minus Q to the n, Q squared sub n squared. Okay, so this is a natural thing to do if you have some Q series and you can't do what you want to do with them, is transform them. And now subtracting gives something nice. So P sub O of Q minus P sub E of Q is this generating function, 1 over Q squared infinity, times this sum. And if you just investigate this term by term, you can see that the coefficients are all non-negative. And in fact, positive when you want. So each sum n clearly has non-negative coefficients. So when n is odd, this 1 minus Q to the n here cancels with some term here. So when n is odd, there's a 1 minus Q to the n in this product in the denominator, and that cancels. And then everything is now negative. And when n is even, of course, then you can cancel with some term in this Q squared sub n. Okay, so moreover, we want positivity, and this is easy also. So for n equal 2, the summand is this. So I separated out this 1 minus Q just to emphasize that 1 minus Q is 1 plus Q squared plus Q cubed and so on. So we always get a positive coefficient when the exponent is at least 6. Okay. And then we can just check by hand for n less than 6, and we see that the positivity holds for n not equal to 2. Okay, so that implies the result. A few remarks. So that was pretty elementary if you understand partition theory and Q-series transformations. So this is an important one, I think. The classical Q-series transformations are still very useful. Like I said, when we naively computed the generating functions and looked at the difference and couldn't prove what we wanted to prove. But once we transform the Q-series, then everything works out very nicely. And probably the most important example of this is with Ramanujan's Mach theta functions. Take the third order Mach theta functions, for example, of Ramanujan. Those are just Q-series, and you can't do anything with them. But once you have Watson's transformation, then you can rewrite them as Appel-Lurch series, and then you can say a lot about them. So there's already been some follow-up work on this. So my collaborators, Byungchan Kim and Eunmi Kim, obtained similar biases in other arithmetic progressions. So their paper will appear soon if it hasn't already, called Biases in Integer Partitions. So the parity bias I just described involves congruence classes 0 and 1 mod 2. And I believe, I'm not even 100% sure, but I think they looked, the two Kims looked at congruence classes 0 and 1 mod m. Showed that the number of partitions with more parts congruent to 1 mod m than 0 mod m is always bigger than the number of partitions with more parts congruent to 0 mod m than 1 mod m. And honestly, I wouldn't be surprised if this is true for any arithmetic progressions. If you look at the progressions mod m, 1, 2, 3, 4, up to m, that the smaller residue class always dominates. I've seen no results on that. Okay, I know this is a number theory seminar, and a lot of people are talking about all sorts of different kinds of modular forms. But it looks like to me like the generating functions P, those should all be Q's there. Sorry about that. So P sub O of Q, P sub E of Q, and P sub O of Q minus P sub E of Q. These all appear unrelated to modular forms, Mach modular forms, mixed Mach modular forms, false theta functions, and all the things we're used to seeing.
So Jeremy, when you say they appear unrelated,
yeah, I'm going to say more about that, but you can go ahead.
I was just wondering if you did any numerical experiments, like, well, modularity,
I know what you're talking about.
Okay.
Yeah, but I didn't do that. So what appear means to me is that I look at Bailey pairs and Q-series transformations, and I don't see any way to rewrite them in terms of like Appel-Lurch series or indefinite quadratic forms or something like that.
Yeah, I think if you wanted to test if they are related to modular or Mach modular forms, you could look at the radial asymptotic expansions near roots of unity, and if they have sort of, this is like what Ramanujan said in his letter to Hardy about his Mach theta functions, is that if you take a typical QRPG geometric series, the asymptotic expansion is just this awful infinite thing. But just for the Mach theta function ones, they close off into finite expansions, and it's usually kind of clear that it looks different if it's.
Yeah. I know about that. I just didn't do it.
Oh, okay. Yeah, I was just curious if you had. Yeah. Okay.
Okay. Any other questions? Okay, so let's move on to more on theorem 2. So this is where there's some heavy duty combinatorics, which I'll try not to get too much into, but this is shown in 2 steps. So there are 2 inequalities we prove. So first, 2 times p sub e of n is less than p sub o of n, except for n equal 2 and 4. And the second one is that 3 times p sub e of n is bigger than p sub o of n, except for n equals 1, 3, 5, and 7. So each part is done using an intricate injection, so intricate to say the least in one of the cases. I'll say more about that soon. And I'll just give the idea for the first part. This is the easier one. So there's some combinatorial setup here, so I hope you bear with me. So first I want to talk about Frobenius partitions, Frobenius symbols. If you don't know about Frobenius symbols, you should. So let's take A and B to be 2 sets of partitions. And this definition is due to Andrews. So I say recall, hopefully some people know about this already. A generalized Frobenius symbol of type AB and weight n is a two-row array of this form. So A1, A2 up to AK, B1, B2 up to BK. So the top row is a partition in the set A, and the bottom row is a partition in the set B. And for the weight of this thing, we just add all the entries of this two-row array, but then the tricky thing is we also add 1. So we add all the entries plus the number of columns. And if you understand how these are related to ordinary partitions, you understand why we do that. Okay, so these are generalized Frobenius symbols. Just some more notation. So let the script F sub AB denote the set of Frobenius symbols of type AB, and let capital F sub AB of n denote the number of Frobenius symbols in the set script F sub AB with weight n. Okay, so this is more than just playing around these Frobenius symbols. This has some motivation. Generalized Frobenius symbols can be used to represent a number of types of well-known partitions. So the classical example is that if D is the set of partitions into distinct non-negative parts, then F sub DD of n is just equal to the number of ordinary partitions of n. And this is fairly easy to see from the Ferris diagram. You cut out a diagonal and then you read the columns and put those in the top row, and then you read the rows and put those in the top row, and read the columns and put those in the bottom row of your two-row array. And the reason we add 1 to each column is because we cut out the main diagonal of the Ferris diagram. Another example is if O is the set of over-partitions into non-negative parts, then the number of over-partitions of n here, P bar of n, is equal to this kind of Frobenius symbol, so F sub D O of n. So we have a partition into distinct non-negative parts in the top row and an over-partition into non-negative parts in the bottom row. So I didn't define over-partitions here. These are just partitions where the first occurrence of any number may be overlined. So I hope someday I won't have to define that. Like we don't have to define partitions anymore. But anyway, that's the definition. Okay, just to say these Frobenius symbols are useful in classical partition theory. And this is our setup here. Okay, so to prove theorem 2, we let D sub E denote the set of partitions into non-negative even parts. And then we let script A, maybe that's cal A, be the set of partition pairs, pi lambda, where pi is a partition into distinct parts, and lambda is a Frobenius symbol in F sub DE, which means we have a partition so I left out a word here. So D sub E denotes the set of partitions into, so that should say distinct non-negative even parts, and that's important, so sorry about that. That should say distinct. Okay, so lambda is a Frobenius symbol in F sub DE, where 0 always occurs in the top row. And then we let B be the set of partition pairs pi lambda, where lambda is a Frobenius symbol again in F sub DE, where 0 is always a part of the top row. And we have an extra restriction and a relaxed condition. So the relaxed condition is the largest part of the top row may be overlined. And the extra condition is that pi is a partition into distinct parts not equal to L of lambda, where L of lambda is the number of columns in lambda. Okay, so that's the combinatorial setup. So why did I make all those definitions? This is because it turns out that if I look at this generating function, so the sum over all pairs in B, q to the weight of pi, which is just the sum of the parts, plus the weight of lambda. So this absolute value symbols means the weight, minus the sum over all partition pairs in A, q to the weight. This ends up being P O of q minus 2 times P E of q. So you can go through the analysis. This is the generating function for this first part, so I won't go into detail about that. You can think about it if you want. And this is the generating function for the second part. Okay, and then we recognize these as related to generating functions for P sub O of q and P sub E of q. So this is 2 times P sub O of q minus P E q of q minus P O of q, which is P O of q minus 2 times P E of q. Okay, so notice here I use the transform generating functions to study these inequalities again. Okay, and here's the coefficients. So we have a minus at q squared q fourth. So if you remember a couple slides back, I said we prove this equality for n, not this inequality for n not equal to 2 and 4. This is the reason, because it doesn't hold when n equals 2 and 4. Otherwise, it's a normal growing q series. And just to show you that, I went way out to q to the 20th, q to the 21st, where the coefficients are 82 and 107. All right, now to prove the desired inequality, we have to give an injection, which I'll call phi, from a sub n to b sub n for n not equal to 2 and 4, where the subscript n means that the weight is n. Okay, hopefully you see what I'm doing here. Once we prove this injection, because P sub O of q minus 2 times P E of q is equal to this generating function up here, if we can have this injection, then we will have the inequality. Okay, so let me say a little bit about this injection. You don't need to follow all the details, but the point I just want to make is that when doing these injections, what happens is there's some kind of standard mapping you want to do, and it doesn't always work. And then so you have to look at the exceptional case or an exceptional family of cases and then do something for that family. And then if that doesn't quite work, then you have to do another little tweak. And if that doesn't quite work, then you have to do another little tweak. And well, if you're on the right track, then eventually you can chase down all these different cases and make it work. Especially in this case, because the coefficients of the difference grow pretty quickly. And so the difference coefficients and the difference functions are pretty big. And so you have a lot of room to do these injections. Anyway, so let's let pi lambda, be a pair in a sub n, and we'll define the injection as follows. So the image of pi lambda is pi prime lambda prime. So if the number of columns of lambda is not a part of pi, then we can just use the identity map. Right, so this is pretty much the map we want to do. So remember, in A, we have the restriction that 0 has to occur in the top row. And in B, we have the restriction that 0 has to occur in the top row, but we're allowed to overline one part, and the number of columns can't be a part of pi. So if the number of columns is not a part of pi, then we just apply this map. If the number of columns is a part of pi, then there's something pretty standard we can do, but this only works if pi has at least 2 parts. So I'll say what this is. Then pi prime is the Frobenius symbol obtained by overlining the top leftmost part of lambda. So this is kind of for bookkeeping when we do the inverse map. We know we've applied case 2 here. And then pi prime is constructed by deleting lambda, L of lambda from the partition and adding L of lambda to the largest part among the remaining parts of pi. Okay, so those are a lot of words, but just let me show you an example. So here we have pi lambda. The number of columns here is 2, and 2 is a part here. So we can't use case 1 and use the identity map. And so what we do to fix that is we just remove this part 2, add it to the largest part remaining in pi, and then overline here in the upper left. Okay, and this overlining again is some bookkeeping which tells us that we've done this operation. Okay, but we can only do this when pi has at least 2 parts. Because if pi has just 1 part, then we can't take that part out and then put it back. Otherwise, it would still be a part. That's equal to the number of columns of lambda. All right, so that almost works in every case, and the case 3 and case 4 are just just tracking down the remaining cases. So right, if pi just contains 1 part, and that's equal to the number of columns of lambda, then we have to do something else, as I said. And actually, there are 2 cases. So first, if that number is bigger than 1, then we do this. I don't want to talk about all this. It's just the point I just want to make is that there are some extraneous cases you have to mess with here. So this is case 3, and then case 4 is this, where pi just contains 1 part. It's equal to the number of columns of lambda, and that is 1. Okay, in this case, we just make an arbitrary definition. and this is what it is. Okay, so hopefully that wasn't too heavy. I'm done with all the combinatorics now. Then we make these observations. So first, that phi is defined on all pairs in A except for k equals 0 and 1 in case 4. And this corresponds to n equal 2, 4. So remember the weight is the sum of the entries here plus the number of columns plus the number here. So this is 1 plus 1 for the number of columns plus 2k. So when k is 0, we have nothing, and when k equals 1, we have nothing, right? This isn't even defined for k equals 0, 1. Okay, phi is an injection. This takes some reflection, but it's true. And then this gives the inequality p sub 0 of n bigger than or equal to 2 times p sub e of n for n not equal to 2 and 4. And then one more thing, so this was an inequality, but we wanted strict inequality. And so for strict inequality, we just find some pairs that are not in the image of this map. So some pairs in B. So here they are. So pi is equal to 2, 1, and then lambda is 2k over line 0, 2, 0. Or pi is equal to 2, and lambda is equal to 2k over line 0, 2, 0. And the reason these are not in phi of A is, I don't know how much you want to think about this, but if you go back to the 4 cases, if these are in phi of A, then they come from case 2. That's the only possibility. But in case 2, remember we removed a part of pi, which was equal to the number of columns of lambda, and then added it back to the largest part of pi. But the number of columns of lambdas here is 2. Okay, so there's no way so the largest part here would have to be bigger than 2 for this to work. Okay, so these are not in phi of A. And then you just look at their weights. So this is 2 plus 1 plus 2k plus 2, and then plus 1 for the columns. And that's 2k plus 7, and this has weight 2k plus 6 here. Okay, and so that gives us the strict inequality for n bigger than 8, and then we can just do a check by hand for the other n. Okay, so that's the proof of the first inequality by injection in theorem 2. So let me make some remarks before I go to theorem 3. So the injection for the second inequality, which is 3 times PE of n, is bigger than PO of n. This is much more involved. So there are multiple cases, subcases, and sub-subcases. Officially, there were 3 cases, but then I think each case had case 2 subcases or maybe more. And then I remember one subcase even had like 7 sub-subcases. But eventually we figured it out. But the idea is the same. We want to do some standard mapping or 1 or 2 different standard mappings depending on 2 different cases, but then that doesn't quite work in every case. And so you have to modify it, and then you have to further modify it. But even it ends up working. So we also have a Q-series proof for P sub O of n bigger than 2 times P sub E of n. I won't show you this, but we didn't get one for the other inequality. So for this inequality, 3 times P sub E of n bigger than P sub O of n, we couldn't find a Q-series proof, which is why we had to do this injection in the first place. Okay, so we really didn't need this injection for this inequality, but we needed it for this one. Okay, so maybe we missed something. Maybe there's a nice Q-series proof of this. You can try it if you want, but we couldn't find it, and so had to do an injection. And we did one for this case as well. So I did briefly mention this before, but note that we use the transform generating functions and the corresponding pairs of partitions, right? One partition into distinct parts, and then one Frobenius partition of a certain type. And we didn't at all argue directly with P sub O of n and P sub E of n. We didn't argue with the partitions counted by P sub O of n and P sub E of n to give these inequalities. And so it's a natural question whether you can do this directly. Okay, so that's all I want to say about theorem 2. For theorem 3, let me start with some data.
Jeremy, I have a quick
Yes.
question about theorem
Yep.
2. Do your collaborators in their follow-up, do they have a theorem like this for like 0 and 1 mod m? Like, is it something like it's sandwiched between m and m plus 1 times something?
So I don't believe so. I think what they did is they did theorem 1 and theorem 3. They did the asymptotic result and the inequality, but they didn't do the sandwich theorem.
Okay. Do you know if there's any like numerical like suggesting that, is it always like 2 and 3 or is it something else?
Yeah, so I have no clue. Yeah, I haven't really studied their paper, and the best of my knowledge, it's like I said, they just do the inequality and then they do some asymptotics. But as far as putting this between like 2 times P sub E of n and 3 times P sub E of n, I don't know if they did that or not, and I don't think so. But anyway, the paper's online, you can check.
Okay, thanks.
Okay, so let me start with some data for theorem 3. So for some various n, we compute the ratio p sub O of n divided by p of n. So here p of n is the number of ordinary partitions of n. Compute the ratio p sub e of n divided by p of n, and then the ratio p sub O of n divided by p sub e of n. Okay, so this looks to be converging to some numbers. And what are these numbers? So this is what we show. So p sub O of n is asymptotically 1 divided by the square root of 2 times p of n, and p sub e of n is asymptotically square root of 2 minus 1 divided by square root of 2 times p of n. Okay, which also shows that asymptotically the number of partitions with an equal number of even parts and odd parts is 0, because this sums to 1. And so this is pretty nice, I think. So 70.7% of all partitions of n asymptotically have the property that there are more odd parts than even parts. Okay, so that's again a nice clean result. So this is what we show, and of course to get the ratio of p sub O divided by p of e, we just divide. Okay, so I'm not the world's biggest expert on asymptotic analysis, so I won't go into too much detail about this. So we use Ingham's theorem. I didn't write down Ingham's theorem. Hopefully some of you know what that is. But the point is we need to do two things. We need to show that the coefficients are weakly increasing in our generating functions. So that's the first thing. I'll talk about the second thing later. So we show that p sub O of n and p sub e of n are weakly increasing sequences, just eventually. We don't need it true for all n. The latter holds for n bigger than 5. So how do we do this? Sometimes these can be tricky. I've seen cases where it's not obvious and you need to construct some clever injection, something like that, to prove the weakly increasing property. But the first thing to try is just to multiply the generating function by 1 minus q. So if your generating function times 1 minus q has non-negative coefficients, then your sequence is weakly increasing, right? So this is what we did. In the case of PO of q, this is obvious. Just look at this generating function. So the 1 minus q cancels the 1 minus q here in the denominator of this in this q semicolon q squared infinity. The 1 minus q's cancel, and then this obviously has non-negative coefficients. There's nothing to say there. This is less obvious here because we needed this, when n equals 1, we needed this 1 minus q to cancel with the 1 minus q here. But if we multiply through by 1 minus q, then that 1 minus q is no longer here in the denominator to cancel. So I had to do something a little bit clever in this case. For n bigger than or equal to 2, we're okay. N bigger than or equal to 2, we obviously have non-negative coefficients here. All right, so I said that already. The first series obviously has non-negative coefficients. And for n bigger than or equal to 2, the nth sum end of the second series has non-negative coefficients. And so for n equals 1, we had to use a q series identity. So I didn't write down again what that is. I think it's known as Sylvester's identity. It expands an infinite product as a series. And this is what we end up getting. Okay, so this is n equals 1. The term that the n equals 1 sum end, and it looks like this. So minus q minus q fifth plus q squared times 1 plus q squared divided by 1 minus q squared plus this. Okay, and so you see here everything is non-negative. And this starts at n equal 2, so this doesn't start right away, and you have these few negatives at the beginning. But anyway, this is eventually non-negative. It's true for n bigger than or equal to 6. All right, so that's the first ingredient you need for Ingham's theorem. It was not too hard in our case. The second thing we need is to study some asymptotic expansions. So we need to look at PO of e to the minus z and PE to the minus z, PE of e to the minus z as z goes to 0. So this is what we showed. So these asymptotic expansions. And then Ingham's theorem, you just apply it, and then it translates into these asymptotics. In the case of p sub O, for example, we get 1 over 4 times square root of 6n, this exponential, and you just compare with known asymptotics for p of n, and you get the result. So let me say very, very briefly how we get this. We just have a simple q series, which appears to have no relation to any kind of theta function or Mach theta function or anything like that, or modular form. But what we can do is use the constant term method. I'm not sure it's called the constant term method, but we use constant terms. So we use the fact that p sub O of q and p sub e of q can be written in terms of this function. So g sub b of q when b equals 0, 1, and minus 1. So this is 1 over q squared infinity times this thing. So if we go back and look at the generating functions for p sub O and p sub e, it's constructed using these things. And then G sub B of Q, it turns out, can be expressed as the following constant term. So I'll just show you this for B equals 1. So when B equals 1, this is the constant term in a theta function, so Jacobi theta function, times these Q Pockhammer symbols. And so then the theta function we can study using facts about Jacobi theta functions. And this part we can handle using quantum dilogarithm, asymptotic expansion for quantum dilogarithm. So I say this very, very vaguely without giving any details. Just say then we then apply facts about theta functions and the quantum dilogarithm. And that gives us those asymptotic expansions. Okay, so that's theorem 3. No questions this time. All right, so I have about 15 minutes left, and I wanted to talk about some further work and some conjectures. So first, it's natural to wonder about this kind of bias, parity bias in other types of partitions. And we did some computations. So one natural thing to look at is partitions into distinct parts. So if you let D sub O of n and D sub E of n denote the number of partitions in distinct parts having more odd, respectively even parts than even, respectively odd parts. Then just by computation, we found that D sub 0 of n is bigger than D sub E of n, but for n bigger than 19. So inequalities like this that start very late sound tricky to me to do combinatorially. And using generating functions, we didn't get anything particularly nice when we studied these generating functions. There was some kind of double sum Q series, which are harder to handle. So we just kind of left this. And recently someone sent me a paper by Dastidar Banerjee and Bhattacharjee, where they announced a solution to this conjecture. So they announced a proof. I haven't really read the paper, so I'm just saying announced here. But presumably it's correct. Okay, and then instead of parity bias, you can ask about other kinds of biases. So you can do this with any kind of statistic on partitions. We just use odd parts and even parts. One quick example is we did this with overpartitions, and we looked at the number of overpartitions of n with more non-overlined parts than overlined parts, and compare that to the number with more overlined parts than non-overlined parts. Okay, so here there's no unexpected bias or of any kind because the non-overlined parts can repeat. So obviously P sub U of n, P bar sub U of n is going to be much bigger than P bar sub O of n because overlined parts can't repeat. But we could still say things about it. For example, if we look at the difference, does it count something nice? In this case, it does. So it's equal to the number of overpartitions of n, where the number of non-overlined parts is at least 2 more than the number of overlined parts. And this is really easy to prove. I won't go through it, just use some Q-series manipulations, but I wanted to show you that sometimes these differences, even though the inequality is obvious, may be counting something interesting. Okay, so I gave an example here, but I don't want to say too much about it. So here are the 8 overpartitions of 3. The number with more non-overlined parts than overlined parts is 4. The number with more overlined parts than non-overlined parts is 2. The difference is 2. And then the 2 overpartitions with at least 2 more non-overlined parts than overlined parts are 2 plus 1, which has 2 non-overlined parts and 0 overlined parts, and 1 plus 1 plus 1, which has 3 non-overlined parts and 0 overlined parts. It's also natural to consider weighted versions of partition generating functions. So this should be well known to people, but if not, think of some of our most famous Q hypergeometric series that are related to modular forms and Mach theta functions and other number theoretic objects. And these are all weighted versions of partition generating functions. So for example, this is a Ramanujan's third order Mach theta function, which counts the number of partitions of n with even rank minus the number of partitions with odd rank. So this is weighted by -1 to the rank. This partition is weighted by -1 to the rank. This is the overpartition version, and this is weight 3/2 Mach modular form. This was a surprising result of myself and Catherine Bringman some time ago, and it's related to class numbers. Okay, so the coefficient here can actually be expressed in terms of a class number, Hurwitz class number. And then of course there's the Andrews-Dyson-Hickerson sigma of Q, and this is again a weighted partition generating function. So this is the number of partitions into distinct parts with even rank minus the number of partitions into distinct parts with odd rank. Okay, so doing some kind of simple weighting schemes often leads to very interesting functions. Okay, so anytime you study partitions and you have a generating function, it's natural to try these weights and see what comes out. Okay, so hopefully that was enough motivation. And so we considered this weighted version. So I'll say what this is shortly, but just to find these coefficients, a of n by this generating function. So sum n bigger than or equal to 1, q to the n, 1 plus q to the 2n divided by minus q squared sub n squared. So it turns out, and I won't go through the combinatorial details, that a of n is the number of partitions counted by, so I call these lambda, counted by p sub o of n, each weighted by minus 1 to the w, where w is 1/2 times the largest even part of lambda plus the largest odd part of lambda minus 1. Okay, and that just comes from, if you go back to the slide on q to the bn divided by q squared sub n, and what this is the generating function for, and think about what this minus sign means, then it's very easy to see that you get this. But what's interesting is it appears that the following two things are true. First, that a of n is equal to 0 if and only if n is in this finite set. So 3, 5, 9, 17, 20, 23, 24, 26, 28, 51, 125, and 233. So I don't know what those numbers are. I don't know if there's any pattern. I presume not. But this is a bit off the beaten track, let me say, in regards to Q series we typically look at. Either there are just a few zeros at the very beginning, like 2 and 4, something like that, or there's an infinite sequence of zeros which are well behaved, like in an arithmetic progression, or you have almost all equal to 0, something like that. But this finite set, which is not super small and contains some not trivial numbers, is not something I'm used to seeing. And then also a of n has a regular sign pattern, which goes plus, plus, minus, minus, with infinitely many sporadic exceptions. Okay, so I say it appears that. Obviously, I don't know if they're infinitely many or not. We have no proof of this. But this reminded me of something. So I had seen this before, and maybe you recognize this as well. There's something like this in a paper of Andrews on Q series from Ramanujan's last notebook. So in the paper Questions and Conjectures in Partition Theory, this is a very famous paper because it had Andrews' conjectures on the sigma function, which was on a previous slide from Ramanujan's last notebook. That is that it's infinitely often 0 and things like that, which was eventually studied by Andrews, Dyson, and Hickerson using the arithmetic of real quadratic fields. But there's a second part to this paper where he makes some other conjectures. So he talks about some series in Ramanujan's last notebook. So I call these notorious in the abstract. They're notorious because they occur in some identities which are hard to prove, but simple to state. And they also have these weird sign patterns. So Andrews called these a lengthy sign change pattern that alters fairly infrequently. And he made some precise conjectures. So here, example is, there are 4 series in his paper. Here's one of them. So simple looking Q series. And then so the question is, what is the explanation for these almost regular sign patterns? So I wanted to show you some data. So I'm going to screen share a Maple page. So hopefully this won't be too hard to look at. Just follow my cursor if you want. So I have some notes here so I don't have to stare at this too much. Okay, so this is the first series. This is the one here that comes from the parity bias, this weighted version. So you notice that if you go to 233, it's missing. So 232 is there and 234 is there, but 233 is not. There's just a 0 here. That's the last 0 we found. And then after that, the sign pattern appears to be plus, plus, minus, minus, right? So we have minus, minus, plus, plus, minus, minus, plus, plus, minus, minus, plus, plus. And I don't want to say that over and over again, so let me skip ahead to where we don't have that. So if you go down to 300, you have plus, plus, 300, 301, and then 302, 303 of minus, minus, and then 304, 305, 306 are all positive. So we have a plus, a very small coefficient here at 304, plus, and then plus, plus. Okay, so there's 3 pluses in a row, just kind of randomly. And then it goes back to minus, minus, so minus, minus, plus, plus, minus, minus, plus, plus. And then there are, as far as we look, we always find exceptions to this. And they seem sporadic, and I don't know what the explanation is for this. Right, this plus, plus, minus, minus sign pattern is a usual one we used to seeing in Q series and modular forms, things like that. But when there's these little random exceptions, that looks a bit weird. Okay, and then this is Andrew's series. He calls it V1 in his paper. So this is the one I put on the slide, the one it's in Ramanujan's last notebook. So I wanted to look starting at 702. Okay, so starting at 702, we have three minuses, see, minus, minus, minus. And then after that, it just goes plus, plus, minus, minus, plus, plus, minus, minus, plus, plus, minus, minus, plus, plus, minus, minus, and so on. And then the next place that changes is at 877. And so at 877, this is preceded by two minuses, and then we have plus, plus, plus. And after it goes back to minus, minus, plus, plus, minus, minus. And it does that for a long, long time, and then just once in a while, it has this little error. Okay, and then just to show you the zeros of Andrew's function, it has a kind of this finite list of zeros like in the parity bias generating function. So the small list, but the numbers aren't all terribly small, goes up to 198, and it appears there are no more. So I don't know why this is true. I don't know if anybody knows why this is true or how to prove these things about the sign patterns. I wanted to share Andrew's paper now. Oops. Okay, so this is Andrew's paper. So he starts here above equation 4. So hopefully you can see my cursor. So he calls these seemingly innocent Q series. I don't know what makes Q series look innocent or not innocent. But here's this V1, this is one of them. And he makes 4 conjectures. So he says that as n goes to infinity, these coefficients go to infinity, but he notes that the growth is not very smooth. And he gives some sample values. So it's like what I showed you on the Maple page. And he said it appears that standard analytic means are questionable. He suggests that maybe a combinatorial interpretation could help. Personally, I find that somewhat questionable as well. I think some more advanced analytic means are needed. And so he makes 3 other conjectures then. So he says for almost all n, any 4 coefficients are 2 positive and negative numbers. And then he specifies these exceptions that we talked about. This infinite sequence, he says it's an infinite sequence of n's where the 3 consecutive coefficients have the same sign. And he also notes that at this point, there should be a local minimum of the sequence. Okay, and then here are the other 3 series. These are all in Ramanujan's last notebook. They all have these strange sign patterns, or what looks like a regular sign pattern, but then with some random exceptions. Okay, so he says there's great oscillation, and each has a lengthy sign change pattern that alters infrequently. Okay, so as far as I know, no progress has been made on these conjectures. And these are related to some conjectures on parity bias. So I think if you prove one, it can prove all of them. And so if anybody has an idea on that, you should let me know. So one more point maybe to say about this is that there's still some things interesting going on regarding Ramanujan's last notebook. I think Andrews and Berndt put out their last book. And now pretty much everything has been proven all the claims have been proven in Ramanujan's last notebook, but there's still lots of interesting questions around some Q series in there. And this is one of them. What's responsible for these almost regular sign patterns and these zeros that go up to 200 or 300 and then disappear after. Okay, so 1 minute short, but that's all I have. So I'll just say thank you.
All right, well, let's thank Jeremy for a beautiful talk. Any questions for the speaker?
So this is probably a very simple question, but the definitions for PO and PE were strictly more odd than even, right? Strictly more even than odd.
Yeah.
What changes if you allow, rather than strictly greater, just greater than or equal to?
Right, so as I noted, asymptotically, the ones that are equal to don't contribute anything.
Mm-hmm.
And then not asymptotically, it makes the generating functions nicer. And when we did these transform generating functions, everything seemed to just look nicer if we just excluded those. And since asymptotically that was 0% of the partitions anyway, then we just left those out, equal.
Thank you.
Any other questions for Jeremy? Yeah, these conjectures at the end, Jeremy, well, conjecture slash phenomenon to explain, because we don't have a strict conjecture for how often the sign changes shouldn't work or whatever. But yeah, they're very interesting. Does Andrew say anything more about these functions that show up in the Lost Notebook? I mean, he talks a little bit about the sign changes. Does he give any other hints about like what those objects are or anything else they're related to?
No, and that's the thing I forgot to mention, that I think some point way back in the day, I mean, I looked at those and tried to use Bailey pairs and some techniques like that to transform them and write them in terms of things we recognize. And I didn't have any success.
Do you happen to know why Ramanujan was looking at those series, or like where they came from?
I don't. I mean, he has some identities, and Andrews talks about those in his paper. And I think it's in, he has a series of papers called Ramanujan's Lost Notebook. There's 1, 2, 3 up to whatever. I think it's in number 4. Number 4. It's called Stacks and Alternating Parity and Partitions. So combinatorially, it kind of fits in with some other things Andrews was looking at in Ramanujan's Lost Notebook. But as far as these identities, I mean, those Q series, they just sit there in like 2 or 3 identities that are on some page in the Lost Notebook and seem totally unrelated to everything else. And even the proofs, I mean, if you look at the proofs, so if you look in Andrews and Burt's book, they call these innocents abroad, I think. They have a section, and they're just kind of saying these are totally unrelated to other things. And the proofs require some really crazy, like triple sum transformations using Bailey pairs, things you wouldn't expect at all. It's really wild.
Weird, yeah.
So it might be worthwhile going back to look at those and see if they look like they're related to any kind of modular objects, something like that. I mean, I have really no guess. My only guess is that it's the sum of some things and there's some overlapping, and I don't know why that some places you just witness this. But that's very vague.
Okay, great, thanks. Any other questions? All right, well, if not, let's thank Jeremy again.